Right. It gives me great pleasure to invite Professor Mojtaba Soltanalian to come to USTC to give us a presentation and to have a short visit here. Professor Soltanalian got his PhD degree in electrical engineering from Uppsala University. In fact, from my favorite collaborator, Professor Patrick Stoika, as his PhD advisor, in 2014. He's now with the University of Illinois at Chicago. So people were asking, is Chicago safe? He said, it's pretty safe. Before joining UIC, he held, I think, visiting positions mostly, right? With Caltech, with Luxembourg.
Yeah, postdoc fellowships. Yeah.
Right. His research interests lie in the interplay of signal processing, learning. Nowadays, you have to put learning in your talks, and
That's
optimization
right.
theory, and specifically different ways the optimization theory can facilitate a better processing and design of signals for collecting information, communication, as well as to form a more profound understanding of data, whether it is in everyday applications or in large-scale complex scenarios. So Professor Soltanalian is now on the editorial board of signal processing, is a vice chair for IEEE Signal Processing Society chapter in Chicago, and this is hard to get too. He is a recipient of 2017 IEEE Signal Processing Society Young Author Best Paper Award. That means when he submitted that paper, he was under 30 years old, right?
Yes.
Yeah. So Best Paper Award. That's Signal Processing Society Best Paper Award is very hard to get. Okay. But fortunately, this guy, he's 19.
You have time, right?
He has a chance.
So set the clock, 11 years.
Yeah, 11 years. You have the time. That's the goal, to get a Young Author Best Paper Award from IEEE Signal Processing Society. Okay, much
Well, thank you very much for the kind introduction and hosting me. It's a great pleasure to be here. As you can see, this title has basically two parts. One is signal processing and learning with partial information, right? And the other is guaranteed signal processing and learning. And I will talk about both, and we'll try to connect them, a little bit at least. Before we go forward, I should say that a major part of the credit for what we discussed today, the results that we discussed, goes to our collaborators, Professor Lee and Professor Lee Swindelhurst at UC Irvine, and also the great students that I have at the Waveform Optimization Laboratory. They have done great work. We are here. This is the campus. Basically, we are in downtown Chicago. We have a great view, at least. And the campus is actually home to this architecture called the Brutalist architecture. So you can see a different kind of architecture when you come to the campus. And you wouldn't have a hard time to find the campus because it's in downtown Chicago. You're very welcome to visit. And if you want to stay for a longer period of time, we have PhD positions available. Okay, so what is this all about? I want to start with this example of the Netflix challenge, and I think some of you have heard about this. How many of you have heard about the Netflix challenge? Yeah, some have. Yeah. So let me talk about it a little. So recommendation systems, like in those streaming services like Netflix, what they want to do is that they want to make recommendations to users, the things that they are likely to watch, right? And they want to do this based on the ratings that are already available, right? The ratings that the users gave. We have a rating matrix. Let's say MC times P, C is the number of users, P is the number of movies, right? MIJ will be how much user I likes movie J, right? And some of these are available, but we haven't asked everybody about every movie, right? We want to recover the matrix, the entire matrix, right? How can we do that? People use this idea that works pretty fine, the idea of the matrix being low rank, right? The assumption that we make about the rating matrices. And I think it works fine because many people share similar taste in movies, right? So the problem is that from a few entries of this matrix, we want to recover the entire matrix, and the goal is to making movie recommendation to users, right? Now, in my group, we were actually looking for a challenge. We said, what if we are working in a much more strict setting? So in a setting in which you don't have even those few entries, you have comparison among movies, right? You show two movies to the user, say, which one do you like best, right? So the person says, okay, I like movie A better than movie B, right? So you don't have exact ratings, you have some comparison information. Now, can you recover the rating matrix using that assumption of low rankness, right? And we showed that you can actually do that under some conditions, right? And we will talk about this today. But I think this is a good example to see what I will be talking about today. So the kind of signal recovery problems, and also the focus of the talk. So I talked about signal processing with partial information, but you might ask, are you going to talk about all these problems in signal processing that work with partial information? You can do matrix completion, expectation maximization. There are a lot of things that you can do. Not all of them. I will talk about specifically efficient use of one-bit sample data and one-bit comparison information. So why comparison information is one bit? Because if you compare movie A better than movie B or movie B better than movie A, it's one-bit information, right? You can store it as +1, -1, 1 or 0, right? And also one-bit sample data, and all of this is because of this guy, one-bit ADCs. So why are we talking about this right now? So one-bit results have been around for a long time, maybe from the time that people talked about zero crossings in signals. Then when compressive sensing became hot, many people talk about one-bit sampling again. But these didn't have so much of killer applications. Now we already have the killer application for one-bit sampling, and the killer application is actually massive MIMO, and specifically millimeter wave massive MIMO. So you can imagine that when you deal with massive MIMO, you have large scale antenna arrays, right? It might mean that you have many RF chains, perhaps many ADCs, right? And these ADCs, if you work with high resolution ADCs, they have many deficiencies. Actually, they are the bottleneck in implementation of massive MIMO. Because if you need high resolution samples, the ADC will become very slow, right? It is very costly to buy and use in the implementation of massive MIMO, and also it is not very power efficient, right? The one-bit ADC, actually usage of one-bit ADC promises to solve all these three problems, right? The speed, right? The cost and power efficiency, right? Now these are taken from Lee's, plenary. So.
From Brazil.
Yeah, exactly. So why are we doing this? Because this is actually our road to gigabit wireless, right? Now this is an important application, but it's not the only one, right? So what I want to do today is actually talk about several interesting problems under this topic of one-bit sampling and using comparison information that we actually looked at in the past year. Okay. So I will actually talk about a set of problems. I start from more classical estimation problems like data fusion, and also I look at an example in radar, and then I will move to more like fancy problems in like a rating matrix recovery, Netflix problem, and also data clustering. Okay, so let's start with this simplistic setting of data fusion. You have a sensor network, a wireless sensor network that is basically measuring a deterministic parameter. Let's say the temperature in this room, and we have several sensors, okay? Now, temperature theta is being measured. So if you have a high resolution ADC, you will have the temperature plus some noise, right? That is the model we use. Now, this is what you get for high resolution ADC, but in case of one-bit quantization, your one-bit ADC actually compares the measurement with the threshold, right? So you can actually set the threshold, and what you get at the fusion center, so we collect this from the sensors, at the fusion center you get actually the sign of the measurement minus the threshold, right? Higher than the threshold or lower than it. Let's say that you have these measurements, right? So these measurements, if you had a high resolution ADC, what you do is actually you do a maximum likelihood estimation or minimum variance unbiased estimator, or you do actually a BLEU, right? Best linear unbiased estimator. All of these are the same thing. You get actually something like this, a linear combination of the measurements, right? That is basically a function of the variances, right? Now, this is if we knew the signal, right? The signal that is this high resolution signal or high resolution measurement. But we don't know, right? We don't know this high resolution measurement, right? So how can we tackle this problem? So we want to recover this theta, but without the knowledge of Z, the high resolution Z, with knowledge of one-bit sample Z, right? Okay, so this is why we came up with this, we exploited this weighted least squares criterion. So this actually looks at the difference between Z and all theta, all theta multiplied by all one vector, right? This is actually penalizing the mismatch between Z and all theta vector, right? Now, and also it's a weighted least squares criterion because at the core of it you have the inverse of the covariance matrix of noise. So you can work with white noise, you can work with colored noise, different kind of things. And to see why this is very useful, you can actually have two very important observations. One is that if you try to optimize this, right, you also have Z as an optimization variable, right? So you can actually optimize with respect to both Z and theta. It doesn't require the knowledge of Z, right? So you can recover both Z and theta. And another observation that I think is even more interesting and shows how natural this criterion is that if you have Z, right, if you fix Z, if you assume that you have the knowledge of Z, your optimal theta of this criterion, the minimizer theta of this criterion, is exactly the same as the case where you know Z and you apply best linear unbiased estimate, right? So this is a pretty natural criterion to use, right? And it doesn't require you to know Z, right? So how we exploit this? So of course you can optimize with respect to Z and theta, but you can also do something else. You can actually write this as a quadratic function of Z, right? How do you do that? You use this optimizer, right? Theta, and substitute the theta in the criterion. You get a quadratic function in Z, right? And then your problem of signal recovery, right, recovering Z and eventually theta, boils down, well, this is actually not QCQP, this is a quadratic program with linear constraints, right? So you have a quadratic objective, but then you have linear constraints that actually checks the compatibility of your Z with the one-bit comparison information or one-bit sampled in one-bit samples, right? So it tells you that, for example, this omega k is actually the diag of these sign values, right? So you have a diagonal matrix that at its diagonal integers has these signs, right? And when you multiply omega with Z minus tau k, it ensures that Z is, same as the measured Z, is above the threshold or lower than the threshold, right? So it actually it checks the compliance with the one-bit information, and when you're compliant, it actually minimizes the model mismatch. Correct? So you can, with this, you can recover Z, and then you can recover theta, right? Using the same, best linear unbiased estimator that, ML estimator that you had, right? Now, you can actually look at the figures. These don't tell you much, but what they tell you is actually this idea works when the parameter is fixed. It works when the parameter goes basically becomes very small, right? And also, if the number of nodes grows large, you will have much lower and lower. It actually closes the gap between 1-bit sampling and infinite precision sampling. So if the number of sensors grow large, it seems like you don't really need the high resolution ADCs. So it closes the gap. So you get this almost the same performance with the 1-bit ADC. Right? You will see in the radar example. So this is actually a pretty similar problem, but we actually looked at this problem in the context of radar, and I'm hoping that some of you know about how radar works, right? So let me tell you like in a few seconds. So the underlying principle, the most simplistic way to look at it is that the radar transmits a waveform, right? It goes and hits the target. Some of the energy will be backscattered to the radar receiver, right? And you can use two actually data that you have. One is that you know the time difference between your transmission and reception, and the other is the speed of electromagnetic wave, right? With these two information, you can actually recover the distance between you and the target. This is the principle that you can use for localization, basically. Now, how we did this, a study of 1-bit sampling in the radar case, we actually looked at, a similar linear model. So let's say that S is the transmit sequence, a discretized version of your waveform, right? So you're transmitting S1 to Sn, and capital N is the length of your transmit sequence, right? And at the receiver, the baseband signal that you receive is actually something like this: A Hermitian alpha plus epsilon, where basically you're receiving the signal with the scattering coefficient of the current range cell, the range cell that you're interested in, right? It works. It is actually very useful in target tracking scenarios when you have an idea what is the range cell that you're interested in, right? And then not only the signal you will receive, but also shifted versions of the signal, right? And those actually are related to the clutter, so adjacent range cells, right? So alpha 0 is the scattering coefficient of the current range cell. Alpha k is for k not equal to 0 are scattering coefficients of adjacent range cells. And you have epsilon, which actually accounts for noise, right? And we also assume that we know some things about the interference, right? So interference has noise in it and clutter in it, right? So we know the covariance matrix of noise, and also we know the power of the clutter, right? So we are assuming that we know these things, okay? And also we are assuming that noise and clutter, these components are independent. Right? Now, let's look at the classical estimation aspect of this. So what if the signal Y is available, right? If Y is available, you can actually use a mismatch filter to recover optimally, in the sense of mean square error, the alpha 0. So the goal here is actually to recover alpha 0, right? Then when you have alpha 0, this scattering coefficient of the target, you can also move to a detection scenario, right? If alpha 0 is larger than something, you say that, oh, there is a target here, right? Very likely. Alpha 0 is very small, you say that, oh, perhaps there is no target here, right? So you can actually use a mismatch filter, and it actually works linearly on Y, right? So W Hermitian Y over, divided by some scalar, right? And W is also given, it's also like a Capon beamformer, right? So W is given as R inverse S, where R is the covariance matrix of interference. It has both noise and clutter in it, right? Now, this is where we have Y, right? But we don't have Y. We have one bit sample version of Y, correct? Now, how can we deal with this problem? So again, we are using a weighted least squares criterion, right? Let's look at this. So we are saying that we want to penalize the difference between Y and alpha 0S. And it makes sense because this is actually, this is the same thing. It tells you that Y is actually alpha 0S plus some interference, right? And that interference, you are hoping that interference is small, right? So you can actually penalize the difference, the model mismatch basically. So the difference between y and alpha 0 s, and the covariance, the weight that you use at the core of this quadratic objective is R inverse, where R is the covariance matrix of interference, right? So what is the optimal alpha 0 here? So it is something similar to what we had before. So it shows how natural this criterion is. The optimal alpha 0 of this is nothing but what we had here. So you can check it out. You know, if you grab a piece of paper and write it down, you will see that this is indeed the optimal alpha 0 of this criterion, if you know why, right? So this is one observation. The other observation was that this doesn't assume that you know why, right? It optimizes the, you know, the model, it minimizes the model mismatch with respect to both y and alpha 0, right? So you can actually, like before, substitute the optimal alpha 0, right, in the criterion and make it a quadratic objective, right? This is the same criterion, but it is formulated based on y, right? And then you check the compliance with your 1-bit sample data, right? So you are looking at all y that comply with the 1-bit sample data, but also minimize, but you're looking at for the one that minimizes your model mismatch, correct? So you're good here, yeah. Okay, now how do I sell this? So even when we wrote the paper, I thought about how are we selling this, and I think this is actually a very good way to put it. So we are saying that if you use this criterion, you can actually recover y, right? That is actually the baseband receives signal, right? And it opens the way, it paves the way for you to use all these classical results that are already available and use the knowledge of y, the received signal, right? It is like, you know, you're having some sort of way to actually circumvent this 1-bit sampling problem, right? So you actually recover y and say, okay, now recover whatever you want, right? So the recovery of y may not have perfect precision, but remember, here the goal is not to recover y, basically, right? The goal is to recover alpha 0, and that is one parameter, right? That one parameter we can show that you can recover with very good precision, right? And these are some figures that you can look at and see how things work. The message that this figure has mostly, I think, should be that the method works, right? And the other thing is that as n grows large, the length of transmit sequence, we are actually closing the gap between 1-bit sampling and infinite precision sampling, right? So the method works. This green one, this green circle, is actually the true value of alpha 0. It might be a bit difficult to see, right? Or can you see it? The green circle, here, here, here. So they are all gathering around this green circle. Okay. Now we have the black ones are the infinite precision, so infinite precision samples. So you're not using 1-bit ADCs. Then you have the red ones that is the output of our algorithm, and then you have the blue one, which is the output of a Bosgang aided algorithm that I will not discuss here, but I can tell you very briefly what it is. So Bosgang theorem actually gives you a way to connect the covariance matrix of 1-bit sample data and the high resolution sample data, and then you can use that that connection between the covariance matrices to recover alpha 0, right? But as you can see, it's not as good as the proposed method here, the weighted least squares that we are using. And I think the one problem that leads to this is that it should work with one snapshot. So the covariance matrix that it makes is based on one snapshot. It cannot have the quality that actually we are having here. And you can also see that they are closing the gap, right? So the red one is the proposed algorithm. The black one is the infinite precision, right? And you see that as n is going, it's near 100, or even if you specifically if you go to 1,000, the difference is very small, negligible actually. Okay, that's about the classical results. Let's look at these fancy results again. We are going back to the Netflix challenge. Okay, so as I discussed before, so we are looking at this setting that you don't have the exact ratings like in Netflix 0, 1, 2, 3, 4, 5, but you have comparison between two movies. Let's say Breaking Bad and The Fosters. You have seen Breaking Bad, right? Okay. So how can we deal with this problem? So I want to present a 1-bit sampling version of this problem or formulation for this problem. Okay. So how do you do this? So you want to recover a C times P rating matrix. Mij tells you how much user I likes movie J, right? But you don't have this matrix. You want to recover it, right? And we are assuming that there is, there is a small rank, for this matrix. This matrix is low rank, right? And the rank is R. You can ask, how do you know the rank R? In our paper, we actually discussed that you can actually recover or guess or propose a good guess of the rank of the matrix, even using ordering information and comparison information. So there are ways to do that. So you can use those ideas. Now, how do you formulate this matrix recovery problem? Similar to what we had before, you have a matrix M, right? And what you want to present here, formulate here, is that you want to say some of the entries of this matrix are larger than the others, right? So you can vectorize M, this rating matrix, right? And then you can basically multiply this vec of M with row vectors where all of their integers are 0, but two integers, 1 plus 1 and the other minus 1, right? And when you basically multiply this row vector, you will get the difference of two integers of this matrix. Then you can take the sign, right? And what you have is actually your 1-bit information, right? This movie is liked more than the other, right? So you will have this 1-bit observation matrix where with size D times CP. D is the number of comparisons that you make, right? So you collect this sign of the information that you collect is sign of A vec M, right? Or you can say I collect this matrix omega, which is the diagonal, a diagonal matrix with diagonal integers equal to those you collected, sign of A vec of M, right? Now you want to recover M subject to some constraints, and the constraints are like this. The first one is actually compliance with your comparison information, right? So you're looking at all matrices M that comply with your comparison information. So where the integers should, the order of integers are maintained, right? And then you have a rank constraint, right? And also you can add a constraint on basically the interval where the ratings can occur, right? For example, in Netflix, you will say the ratings are between 0 and 5, right? Now, how can we approach this problem, implement this recovery? You can, for example, use a matrix factorization formulation, right? You can say that, okay, so I want to get rid of this rank constraint. It's a nasty constraint, right? So you can use you can say that if M is rank R, you can write it as XY transpose, where X and Y are two tall matrices. The smaller dimension of the two matrices are R, right? So you minimize the difference between M and XY transpose given the constraints that you have, compliance with the comparison information and the interval where the ratings can occur, right? So this is still a non-convex problem, right? But optimization with respect to M, X, and Y separately optimizing with respect to any of these is a convex problem. It's actually a very simple problem. You can see that there is no constraints on X and Y, right? So optimization with respect to X and Y is just simple quadratic minimization. Quadratic function minimization, and then optimization with respect to M is actually a linearly constrained quadratic program, right? And just to show that this I have an example here of, a matrix of rank 3 and size 15 to 20 that we try to recover, and we did recover actually. So this is a true matrix. This is the initialization, right, which doesn't have anything to do with the true matrix, and this is iteration 1, 5, 10, and recover matrix, which I believe is iteration 15, right? And you can see that these are pretty similar, right? Here we assume that we have all the comparisons, right?
How do you know R?
Yeah.
3.
Oh, in this example, we actually generated the matrix so that it has rank equal to 3.
Okay, but in general,
In general, you can actually have a good guess of the rank based on orderings that you have in the matrix. So let's say that you have a matrix whose rows are weighted averages of like 3 vectors or 2 vectors, right? Then the orderings that can occur in those vectors are not, anything. They are actually a function of the orderings of those 1 or 2 or 3 vectors, right? So you cannot have, as many vectors as many orderings as like n factorial, right? If the length is n, right? We actually show that it is like r to the power. So if the rank is r, it should be r to the power 2n or something like that. It is not actually exponential. You can write it and show that it's polynomial actually. Then you can also try to be more conservative. You can add something for the rank, right? Now, how about clustering? Actually, clustering uses this very similar formulation. Clustering, specifically, I'll talk about graph clustering. It has been very useful in big data applications because it is very useful in unsupervised learning. Because it can cluster unlabeled data, and then you can basically have or give them meaning, right? For example, in social media, one example that comes up is the example of political affiliation, right? In the U.S. Democrat, Republican, or something like that, right? And then what they do is actually look at the adjacency matrix of the social network, right? How close people are, how close their ideas are, right? And then based on this adjacency matrix, they try to actually categorize people, right? Based on the connectivity that you have, right? So what clustering does is actually partitions the network, the users in the network, or the nodes that you have, in a way that in each partition you have a perfect connection among those people or those nodes, right? So you have basically a partition of a graph to some complete subgraphs, right? So, and this is the formulation that you get. So let's say that X is a binary matrix where n is the number of users, k is the number of clusters, right? And each row of X has only one 1. So all 0, 1, 1, which tells you how user, let's say, what cluster the user belongs to, basically. So that's what it means, right? And then if you actually grab a piece of paper, write down XX transpose, you see that it actually connects all the people in those clusters. So all the people who have one, let's say in column K, if you write XX transpose, you see that what you get is actually an all-one matrix of that connects all of those people or nodes, right? So what we do is actually try to use the adjacency matrix, right, and match it with XX transpose, right? So when you minimize this, what you get for X is actually the clustering that represents the network, in the best manner. You can also do soft clustering, of course. So it means that you don't need to say exactly this person belongs to that cluster in an exact manner, but let's say 90% to this cluster, 10% to that cluster, and so on and so forth. You'll have the same formulation actually. So I'm not showing the formulations that we had, but I want to show that we could actually do clustering. So especially if the clusters are far enough from each other, you can actually recover the clusters very well using comparison information. What we did was that we started with clustering when you have the adjacency matrix completely. This is the paper that submitted to ICAST this year. And then for Asilomar this year, we actually did the same thing with comparison information. So you don't have the adjacency values exactly, but you know that, for example, the connection of those two people is stronger than the other pair of people, something like that, right? And it is actually very interesting to see that you can actually recover the clusters even with those kind of comparison information. Now I should wrap up that part. I want to also talk a few minutes about guarantees and guarantee signal process, guarantees for signal processing and learning. And I want to start with an example that I like very much. You know that many people right now are working on machine learning, deep learning, these things, and there is a huge debate on guarantees for machine learning. So because these methods like deep learning, it works pretty well in many applications, but you cannot be sure. You cannot provide guarantees that they will work when the time comes, right? And also the interpretability is very difficult, so you cannot interpret the results, right? And I think this example show the difficulty that people have with machine learning, and that's the example of putting a machine learning or signal processing black box in front of a jury in the court, right? So you say that, okay, I have this machine learning black box that is trained for similar crimes, let's say, and we have trained it fully with past data. Now we are using the evidence against this person as the input of this black box. The output is telling that the person is guilty, right? So should the jury believe you or act upon the conclusion that is coming out of this black box, right? So do you think they should do it? No, right? So because there is no guarantee that what this machine is saying represents the reality, right? You cannot be sure about it, and you cannot interpret why the machine is saying what it is saying, right? Okay, so this has well, if you can come up with guarantees, like if you could say, the output of this is in this, given the evidence that you have, is 99% accurate, let's say. So you could provide guarantees or interpret the results. This could have many applications, right? It could have applications in life and death scenarios when you want to make accuracy sensitive decisions. For example, in defense applications, if something is coming towards you, you want to know if it's a civilian aircraft, if it's a missile, and you want to be sure about it, right? So the output of your signal processing system should have guarantees, right? And then you would have applications in artificial intelligence when you need machines that can know how much they can trust their inference. So this is very fascinating. So machines that can go around, make inferences, and they can know if they should act upon the inferences that they made, or they should hold on, if the evidence is good, depending on the environment and the scenarios that are coming by. Okay, so I want to talk about actually a method that we derived a few years ago. And that is basically, that's the reason I'm talking about this. So what we need is signal processing and learning tools that can be trusted. And the angle that we are tackling the problem from which is actually that most of the machine learning problems are in the end optimization problems, right? So if you can have guarantees or enhanced guarantees for optimization problems, it leads to greater confidence in machine learning, right? If you could basically provide this kind of guarantees. So we are actually talking about guarantees for mathematical optimization. That's the angle from which we are tackling the problem. So I want to talk a little bit, so I don't want to get into all the toxic mathematics, so it's like blood all over the place. But I want, in a higher level, I want to talk about this method that we call merit, and I want to say what it is, right? So we are saying that we are breaking the barriers of analytical guarantees because, in mathematical optimization for difficult problems, you usually have, algorithms that people actually derive analytical guarantees for. They say that, okay, this method gives you a solution that is at least this good compared to the global optimum, right? Like it is 70% as good as the global optimum, something like that. And it is not data dependent, it's not problem dependent, right? Because it has to take into account the worst case scenarios, these numbers, these guarantees are not usually that good. They are not very useful. But what we did was deriving data dependent guarantees. So you can see that, for example, in some problems you have perfect guarantees, and then you can be sure about the solution that you get, right? So how do we do this? So this is actually how we do it, so in a higher level language. So in merit we are not trying to solve the problem, tackle the problem exactly, the original problem, but we try to build a sequence of problems that get closer and closer to the problem of interest, right? And another condition is that we know the solutions to those problems. So we are building problems, we are getting closer to the problem of interest, we know the solution to those problems, right? So you can hope that the solution to those problems is also converging to the solution of the problem of interest, right? So that's basically the key idea, right? But how do you derive guarantees? So that's another condition, right? So the condition that you need is that you should be able to derive some guarantee or proximity information, some information on the distance between the solution of your problems and the problem of interest based on the proximity of the problem of interest and the problems that you're working on or building, right? So we have to do some reading here. So it's a little bit involved, but let's start from this variable partitioning idea. So let's say that we have an optimization problem P who has optimization variables x and known variables v. So how do we do this? Let's say that you're looking at this problem. This is basically a linear programming if you don't have semi-definite constraint. This is a linear program, right? So in this, so you have R, Q, and T that are basically the problem instance, the variables that you know, right? And then you have X, which is optimization variable, right? You're doing the optimization with respect to X, right? So you can partition the variables that you have as V and X. So this is the optimization variables. These are the given variables or the problem instance, right? Now the idea here is that, as I said, you should basically try to come up with R, Q, and T and the solution X, and then get closer and closer to the R, Q, T, and X of interest, right? So that's the idea. So you start with, build R1, Q1, T1, R2, Q2, T2, R3, Q3, T3, and you should know the solution for all of these things. So let's just see how we deal with this, okay? So suppose P of V and X is a difficult, possibly NP-hard optimization problem. That's where you need this kind of ideas, and we need an approximate solution, but we have the following conditions to meet, and we can actually meet them. Okay. So the first condition is that you can actually build a sequence of VKs, the sequence of problem instances, or the sequence of problems, right? Such that you know the solution to those problems, right? And the distance between those problems and the problem of interest is decreasing. So this distance function between V and Vk is decreasing, right? So you're getting closer and closer to the problem of interest. Okay? And another thing is constant with the suboptimality guarantee, omega k, gamma k, right? So you should be able to efficiently compute this suboptimality guarantee based on the distance between the problem that you already currently have built and the problem of interest. But if you can do that, you're all set, right? So you have a problem that is converging to the problem of interest, right? And also you have a suboptimality guarantee, which is very likely increasing because you're getting closer and closer to the problem of interest. So we started all this when we were looking at the problem of unimodular quadratic programming. It is basically quadratic programming, but the optimization is done with respect to a unimodular vector, or a vector whose entries are coming from the unit circle. You can also see it in the literature. People call it constant modulus. Okay. And there is no surprise that this is NP hard, so people have studied this already. It has a very difficult optimization landscape. So it has many local optima. It's very difficult to find the global optimum to this. And we tried this idea. So I wanted to show the promise of the idea. So for unimodular quadratic program, many people use semi-definite relaxation, right? This is a method that is widely used. They actually try to formulate this as a semi-definite program, dropping the rank constraint on SS Hermitian, right? And it has a fixed analytical guarantee. It is pi/4. It's about 0.78, right? Now, this is actually the results that we got. Right? So we tried like 20 random matrices R, right? So this is basically you build R, you build a new problem, right? Different sizes, different ranks. And this is the average values of suboptimality guarantees that we got. You should compare this with 0.78, right? It is much higher. It is actually very close to 1, right? Which suboptimality guarantee of 1, it means that you have solved the problem, right? And you can also see that for many of these 20 problems, we actually solved the problem, at least from a numerical point of view. It's very difficult to claim it from a theoretical point of view, but numerically, virtually, we have solved the problem when we get a gamma which is 1 numerically, right? And you can also see that the timing, the average S-tier time over merit time, if you look at these numbers, you can see that the timing is comparable. So I think that's about it. So about merit. So you can actually see more details in this paper. A lot of formulations and a lot of details that you can look at and see how we can exploit merit for the problems that you are interested in. Okay. So to summarize, we talked about signal processing and learning problems that deal with partial information, especially 1-bit sample data and 1-bit comparison information. We talked about the issue of reliability and trust in learning and inference. Specifically, we talked about the idea of merit that provides data-dependent enhanced guarantees for mathematical optimization and learning. And also, we talked about the significance of this, right? So we said that the emergence of such guarantees are game-changing because of applications in decision-making when things are very accuracy sensitive. And also artificial intelligence when you need machines that are next generation, using next generation of artificial intelligence. They can actually say how much they can trust their own inference, right? And that's about it. But I want to end with this remark. So we talked about partial information, and you saw that we can do a lot with partial information. And I think what conclusion you can make, I think, is that working or using partial information is much better than using alternative information, right? Or alternative reality nowadays. And
what, fake news?
Something like that, yeah. Thank you very much. And I would be happy to answer questions.
Well, thank you.
In the learning of partial informations, if you have partially observation like y, can we integrate such information into your formulation, into your method?
So what kind of information? So we already have some partial observation of the vector. That is one-bit sampling, right? So you know that the signal at this time instance, or this, at this specific sensor in a space, is larger than a threshold or lower than a threshold. That is a partial information. But if I understand correctly, you mean that you can use other kind of information,
Yeah,
right?
If I
And
can observe some interest in the Y matrix.
definitely, that is actually a very interesting question. So all of the optimization formulations that you saw, they actually accommodate, if you have further information about the signal, right?
Okay.
So you can add those. Specifically, this is very useful in the matrix rating recovery problem, right? For example, if you have a set of users that are very experienced, right? And they provide you with exact ratings, and for other users, you're using comparison information, right? So it helps you with recovering the rating matrix in the best way, right? I assume using comparison information is very good for inexperienced users because they don't know what exact ratings they should give. But still using some of the knowing some of the interests should help very much, right? Any other questions?
So outside of the Netflix challenge, have you tested any of this this one-bit rating comparison with any other data, or done any other trials to try to prove it out?
So you mean in low-rank matrix recovery, or we haven't tried using real-world data right now just yet. We will do that. So we are expanding the results, and we have some theoretical results that show that you can be successful in some limited settings, but you also have a lot of limitations. Especially one thing that perhaps I can mention, and I think it's very interesting, is that when you use comparison information, you're very limited. So you have CP entries, right? Matrix is C times P, right? You have CP entries, right? How many meaningful comparisons you can have? It's CP minus 1, right? You can have a tree of comparisons. The maximum number of meaningful comparisons is CP minus 1, right? So with CP minus 1 bits, how much can you recover? So that's a very good question if you look at it from an information theoretic point of view. So the rank should be very small, right? And also the quantization bits are used for the ratings. This is used in streaming services even now. So 0, 1, 2, 3, 4, 5. It means that you're using 2 point something bits, right? So you should be very judicious how to use the bits that you have, right? Because you don't have many.
I would like to ask a question. We will see, and we have seen many optimization problems are formulated in the slides. I would like to know the complexity of the problems.
Well, the complexity of problems, they are not very complex. So, because especially in the classical settings that we talked about, you have a quadratic program with linear constraints, right? So I don't have the exact data here, but you can see, check the the information that are available on the web. These are not very complex convex problems, right? So you can deal with these things pretty easily. A concern that you might have, and I think it's a valid concern, is that when you do one-bit sampling, you have very large speed, right? And then in those cases, even a low-cost optimization problem can be very costly, right? So that's the reason we are also working on adaptive, you can call it adaptive scenarios. So how can you use the information you already have, and when the data is coming in as you go by, you can use that to update the information that you have. So you can also do real-time, kind of optimization, adaptive optimization. Then that is a very interesting observation. Yes. Any other questions?
If the problem is non-convex or has a very complex structure, can we still get a guaranteed learning, guaranteed result?
So in the case of low-rank matrix recovery, people have shown that you can actually recover the global optimum if the model mismatch or noise is not very strong. You can recover the low-rank matrix, but I don't think people have studied low-rank matrix recovery when you have comparison information. So that's something actually I think it's open for to a study. So that's something we should consider definitely in the future. Any other questions?
Are you looking for real data?
Sure, yeah, definitely.
David, we have a place to explore the real data.
He's going to
Yeah.
radar systems. He's going to collect a lot of data.
Radar? Or?
Yeah.
That's perfect, yeah. We should stay in contact and see how we can use those, yeah.
Okay. Thank you. Thank you again.
Thank you very much.